Kia ora, team. So to continue off with where we were yesterday, we're talking about complex numbers, and this time I want to just talk about how we convert from rectangular to polar and polar to rectangular. But we're going to start with polar to rectangular, but we're going to understand how we write things in polar form first. So we've got rectangular form, which is the x and the y like going around the rectangle. So we get z is equal to x plus yi or iy. It doesn't really matter which order you write that, but we're just going to write yi for now, but we'll swap it around in a minute. My question is, can we write z in terms of r and theta? And the quick and easy solution is yes. So how? Well, we look at our triangle. Do you notice that there's a triangle? Sorry, I forgot to write the right angle symbol. But it is a triangle. And if I use trigonometric ratios, I can form these really easily. If you notice that if I look at the cosine angle, which is the adjacent over the hypotenuse, I get cosine theta is equal to x over r, because this is the adjacent and this is the hypotenuse. Then I can rearrange and make x the subject and write x equals r cosine theta. Similarly, I can do the opposite over hypotenuse is y over r, which is y equals r sine theta. This is really, really important. So I've written r and theta, made r and theta a function that x can be identified as, and r and theta a function y can be identified as, which is kind of cool. So if I look at writing this in polar form, what I can do is I can look at my function x plus iy, or yi, and write this. X plus yi, I'm just going to swap it around now, iy, because this is just going to get a bit fiddly. And then instead of x, I'm going to use r cosine theta, and instead of y, I'm going to use r sine theta that we got from before. And so now I have written z in terms of r and theta. Yes, there are trigonometric functions, but it's only in terms of r and theta. And then we can factor an r out, and we have r cosine theta plus sine theta times I. And I can rewrite this. And this is where our mathematicians and our mathematicians' laziness comes in. Right? We don't really want to write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 symbols. We want to simplify it. So we look at this thing, and we take the r, the c, the I, the S, and the theta, and we write R cis, which stands for cosine plus imaginary sine theta. And so we read this R cis theta. And this is how we write in polar form in level 3. So cis is not a new trigonometric function, it is a contraction of cosine theta plus I sine theta. And that's quite powerful. And so if ever you're given the radius and the angle, you call it r cis theta, and that is written in polar form. Now what I'm going to do is I'm going to show you how we convert from polar form into rectangular form. Okay, let's have an example. First we'll write something in polar form. So we have this 2, this pi on 3. We don't know what x and y are, but we're going to work them out. Notice that the radius is 2 and theta is pi on 3. So in polar form, z equals 2 cis pi on 3. Now what I'm going to do is I'm going to convert that. Notice that since z equals 2 cis pi on 3, and I know that x equals r cosine theta and y equals r sine theta, I can write z equals x plus I times y. And then I can just work these out on my calculator for now. And then when we get into another Zoom call or in a class, I'm going to talk to you about how we do this a bit better. But we type in 2 cosine pi on 3 into our calculator. It gives us 1. And we type in 2 sine pi on 3, and it gives us a really terrible decimal. 1 and 1.732, so on and so forth. It's a long decimal. We're going to talk about this a little later. I don't mind if you write it in decimals for now, but we're going to change that very quickly. Because in fact, it is root 3. The square root of 3 is 1.732 and so on. And so I've converted something from polar form, which was 2 cis pi on 3, to rectangular form, which is 1 plus root 3i. I hope that was helpful. I'd like to have a call to talk about this a bit more, but I hope this was illuminating. Thank you.